Okay, our next topic is energy of the system of particles. Suppose we have a, let's suppose this is my coordinate axis, this is x-axis and this is y-axis. And we have a system which consists of n particles. Let's say this is particle 1, this is particle 2, this is particle 3, up to let's suppose this is particle n. This is the nth particle. And this particle has a mass m1, this is a mass m2, this is a mass m3, and finally this is a mass mn. Now I consider two particles. Let's suppose this is the ith particle in this system and this is the jth particle in this system. Then this particle has a mass mi, okay, and this particle has a mass mj, such that the position vector of this particle mj from the origin is rj, and the position vector of this particle I from the origin is ri. Now, in order to calculate the energy of the system of particles, what we are doing, we are moving this system. Let's suppose this system is initially here. We are moving this system from this point. Let's suppose this is my position 1. Like I can say that this is the position of the system which is represented by this 1. And I am going to move this system from this position to somewhere here. Let's suppose this is the second position. So I move the system from this position to this position. So now in moving the system from this position 1 to this position 2, we are exerting some external force, okay. This is the external force which is acting on this system. Here, due to this external force, this system is moving from this position 1 or this configuration 1 to configuration 2. So apart from external force, there are some internal forces among these particles. So as a whole, we have two kind of forces acting on this system, which is one is the external force and the other one is the internal forces. So the total force acting on this system is the sum of these two forces, which we already discussed in our previous lecture. Now I consider the ith particle first. Consider the ith particle. Okay. So if I consider the ith particle, then the total force acting on this ith particle is the net force acting on ith particle, which I represent by this Fi, okay, and this net force is basically a sum of two forces. One is this external force which is acting on this ith particle, and the other forces are the internal forces, like the forces exerted by this jth particle on ith particle, this m3 particle on ith particle, and this m2 particle on ith particle, m1 particle on ith particle, like all the other four particles which are inside this system. These particles exert a force on this ith particle, which is represented by this F internal. So the total force acting on ith particle is the sum of two forces. One is the external force which is acting on this ith particle, plus there are internal forces, Fij internal. Sorry. So these are the forces, these two forces, like external force and internal force. These are the forces acting on ith particle. Now similarly, these forces are acting on this ith particle. Due to these forces, this ith particle move from this configuration 1 or this position 1 to this configuration 2. So the work done in moving the particle which particle? The ith particle, okay? From configuration 1 to configuration, or from position 1 to position 2 is, which I represent by this work done W12, okay, which is equal to integral, the limits of the integral is from configuration 1 to configuration 2, and we know that work done is basically equal to integral of f dot dr, okay. So here the force is the total force acting on ith particle dot t distance. Let's suppose the distance traveled from this configuration 1 to configuration 2 is represented by dri. This is the distance. So this is the work done in moving the ith particle from configuration 1 to 2, which is equal to the limits of the integral are from 1 to 2, like moving the integral ith particle from this position 1 to 2 position 2. So the limits are from 1 to 2, and then we have work done by definition of work done is, which is integral of f dot dr. So it is an ith particle, so we have fi dot dri. But we know that the net force acting on the ith particle is basically a sum of two forces, okay, from equation 1, okay. So here if I put the net forces from equation 1 here, then instead of Fi I will put Fi external, okay, plus sum over j Fij internal, okay, dot dri. So these are the forces, so I have to put a vector sign here. Now if I apply this integral this separately, then this equation can be written like this: integral from 1 to 2, we have Fi external dot dri, okay, plus integral from 1 to 2, we have sum over j Fij internal dot dri. This is the net work done. So the work done in moving this particle, ith particle, okay, from position 1 to position 2 is this one. Now I have to remove this limit. I have to bring this summation from inside of the integral to the outside of the integral. So our final expression will be, the final expression for the work done in moving the particle from configuration 1 to 2 will be W12, which is equal to integral from 1 to 2 Fi external dot dri plus sum over j integral from 1 to 2 Fij internal dot dri. So this is the expression for the work done in moving the ith particle from position 1 to position 2. Now this is for the ith particle. Now here I will explain the work done on individual particles, okay. Suppose the work done in moving particle 1, here this 1 in this bracket represent the particle 1, okay. So the work done in moving this particle 1 from position 1 to position 2, or from configuration 1 to configuration 2 is integral from 1 to 2. Now instead of I will put 1, and we have external dot dr1, okay. So instead of I will replace I by 1. So here I replace I by 1, which is for particle 1 in this equation, plus we have sum over j integral from 1 to 2. Now instead of I will put 1, j internal dot dr1. this is the work done in moving particle 1, like particle 1 from configuration 1 to configuration 2. So this encircle represent configuration. So the work done in moving particle 1 from configuration 1 to configuration 2 is given by this relation. Now work done in moving particle 2 from configuration 1 to 2. Okay, this is now particle 2. In moving particle 2 from configuration 1 to 2, in moving particle 2 from position 1 to 2. So the position is from 1 to 2. Now instead of I in this equation, I will put 2 now. I will replace I by 2, so it will represent the work done in moving particle 2 from position 1 to position 2, which is equal to F2 external dot dr2 plus sum over j F2j internal dot dr2. So this is the work done in moving particle 2 from configuration 1 to configuration 2. Similarly, in moving particle 3 from position 1 to position 2 is represented by this. So this 3 in this bracket represent the particle number. So this is the work done in moving particle 3 from position 1 to position 2, which will be equal to, so I replace I by 3 in this equation now. So we have 1 to 2 F3 external dot dr3 plus sum over j F3j internal dot dr3, and so on. So we have, there are how many particles? N number of particles. So this line will goes for n terms. Now the total work done, how we will calculate the total work done? So work is a scalar quantity, so work can be aided by simple mathematical rules. So in order to calculate the total work done in moving this whole system of particle from this position 1 to position 2 can be obtained by adding all these equations, because work is a scalar quantity. So we have to calculate work done in moving, we already calculate the work done in moving particle 1 from 1 to 2, and this is the work done in moving particle 2 from position 1 to 2, and this is the work done in moving particle 3 from position 1 to 2. And similarly, the work done in moving particle nth, let's suppose from position 1 to 2 will be equal to 1 to 2 Fn, okay, external dot drn plus sum over j integral, sorry, there is integral 1 to 2, sorry, there is integral. So integral from 1 to 2 Fnj internal dot drn. So this is for the inner particle. So in order to calculate the total work done in moving this whole system from this configuration 1 to configuration 2 can be obtained by adding the individual work done. So individual work done are given by this relation. So the total work done is total work done from 1 to 2 will be equal to work done in moving particle 1 from position 1 to 2 plus work done in moving particle 2 from position 1 to 2 plus work done in moving particle 3 from position 1 to 2, and similarly and so on, and finally we have work done in moving particle n from position 1 to 2. Now we know that work done in moving particle the system from position 1 to 2 will be equal to, now the work done in moving particle 1 to 2, 1 from position 1 to 2 is given by this one. So we have integral from 1 to 2, we have F1 external dot dr1 plus we have sum over j integral from 1 to 2 F1j internal dot drj, and then we have this plus sign, and then we have work done in moving particle 2 from position 1 to 2, which is this one. So I will put it here, work done in moving particle 2 from position 1 to 2 is F2 external dot dr2 plus sum over j, the integral from 1 to 2 F2j internal dot drj. Similarly, we have work done in moving particle 3 from position 1 to 2 and so on. So we have many terms here, and finally we have this final terms like the inert particle in moving from configuration 1 to 2. So we have the final expression is the final term is integral from 1 to 2, and we have this is integral from 1 to 2. We have Fn external dot drn. So there is a vector sign also notation here with every terms because these are the vectors quantity. So I forgot it here. So these are vector quantity plus sum over j, and then we have these terms are also here, and we have integral from 1 to 2 Fnj internal dot drn. Now if I look at here, this term, these are integrals, okay, from 1 to 2, 1 to 2, 1 to 2. Here we have only differences. Here we have 1 1, here we have 2 2, here we have n. So I can replace this whole terms on the first row here. So the total work done in moving the system from 1 to 2 can be written as. Now this whole terms, this one, like I will encircle it so that yes, in these terms, the terms in this circle line, I can replace it by summation, okay. So we have sum over I, if I external dot dri. So this whole terms like this nth terms, n order terms, like this is 1 2 and up to n. So this nth term can be replaced by this summation such that I started from 1 up to n. Similarly, we have the terms here which I encircle by this green marker. So these I can replace by another sum, which is, so one sum is j, so another sum is I, and one sum is already there, which is j, okay. So we have this integral from 1 to 2 Fij now internal dot dri. So here we have integral also from 1 to 2. So here this whole terms I replace it by this summation. So if I expand this sum, like if I use I is equal to 1, then we have this term, plus I is equal to 2, then I have this term. If I is equal to n, then we have this term. Similarly, if I have I is equal to 1, if I put it here, I get this term. And if I put I is equal to 2 in this term, then I get this term. And similarly, up to so on. And finally, if I put I is equal to n, here I get this term. So here I is equal to started from 1 to n. So overall, I can write this equation is work from 1 to 2, which is equal to sum over I integral from. Now here we have one terms like integral from 1 to 2 Fi dot tri, okay, which is equal to and this is the external force, okay, dot dri plus, and then we have another sum over ij. Now these two sums I replace it by a single sum, where this summation represents the summation over ij. Okay, this summation here, like I wrote this term as it was written above. Now here I replace these two sums by a single sum, which is summation over ij, and then we have integral from 1 to f ij internal dot dri. Now the only difference is that if I use this double summation, then we have to use this condition that I is not equal to j, because the self interaction between particle is not possible. Like ith particle does not exert a force on itself. Similarly, jth particle does not exert a force on itself. So we have to exclude this term. Now this work done in moving the whole system from configuration 1 to 2 include two terms. One is this one and the other term is this one. Now this term comes from the external forces and this term comes from the internal forces. So overall I can write my work done in moving the system from this position 1 to 2, which is equal to, now the total force acting on the system. So the total force is Fi, okay, dot dri. This total force is basically a sum of two forces. One is this one and the other one is this one. So this total force is basically equal to the sum of two terms. One is I, sum over I, integral from 1 to 2 Fi external dot dri, okay, plus one term is this one, sum over ij, such that I is not equal to j, and we have integral from 1 to 2 Fij internal, okay, dot dri. So we have these notations here. So this is our final expression. Like the work done is equal to the sum of two forces. One is external force and the other one is internal force. This is the external force, work done due to external force, and this is the work done due to internal force. But these two forces are basically the sum of two forces. So the net force is Fi net on the whole system, which is Fi net, which is equal to the sum of two forces. So I wrote this term extra because I already mentioned here the net force on ith particle is basically the sum of two forces, this and this. So if I have to calculate the work done, I have to multiply the both side by dri and this side also by dri. So this will give us the work done due to net force, and this side we have the work done due to external force, and this is the work done due to internal force. So both have the same meaning. This is the net force and this is also the net force. So here we have this net force, okay, this is the work done due to net force, and this side we have also the net force, because the net force is the sum of two forces, external force and internal force. So I will stop my video here. In the next video I will proceed further from this point. Thank you.